Oxidizing agents and reducing agents. All right, so we talked about recognizing redox reactions by looking at the oxidation numbers. Right? If those oxidation numbers change, electrons are being transferred, it's a redox reaction. Just think about these reactions just a little bit right now. So here I have two cases. Let me turn it to the red pen. No, stop it. All right, so here I have copper ion, right, and that's blue. So it's aqueous copper ion with zinc metal, which is silvery colored. Here I can have the opposite. I have zinc ions, right, which are clear. And I have copper solid, which is coppery colored. Right? Okay, so if copper is reduced, right, he can get his electrons from zinc and we'll have a reaction. If the reverse is true, copper can be oxidized and give his electrons away to zinc. And if you think about it, it can't be both, right? Nature wants to go one direction if it can. And so what happens is when I put these two guys together, you can see that copper wants to be reduced. The zinc metal is oxidized and the copper metal is not oxidized and the zinc ion is not reduced. So copper wants to be the solid, if that makes sense. So here's the balanced chemical equation that shows this. Let's just identify some stuff. So zinc starts at oxidation number of 0, zinc solid. Copper will be 0. This guy, sulfate, SO4 2-, he appears on both sides, and he's what we're going to call a spectator. We'll talk more about this next time or later. And he's not important. He doesn't do anything. He just watches, so we don't really care about him. He just kind of makes things look complicated. So this will be zinc or copper 2 and zinc 2. And so if I go from zinc to zinc 2 or copper 2 to copper 0, we can see that we have redox reactions, right? They're changing. So zinc to +2 is losing electrons. That's oxidation, becoming more positive. 2 plus to 0 is gaining electrons. That's reduction. Okay, and so on an atomic level, right, zinc metal is losing electrons. It's donating it to copper 2 in solution, and you're getting copper. It's not this. It's not a coppery color when it forms like this. It's sort of a black-looking thing, but that's what's going on. Here's another example. This time we have copper solid with silver ions, making copper ions again, right? Copper ion is +2, is blue, and silver solid. And so in this case, it goes the direction we've seen, and you can see that the silver metal is forming, and can't quite tell, but eventually the copper color is getting bluer, isn't it? Because we're taking copper 0, which is copper colored solid, we're turning it to copper +2, right? So that's the oxidation reaction. This is blue, so we expect the reaction or the solution to become more blue. I think with the, yeah, we believe it. So this is silver +1, and he's going to silver 0, so that's this way. All right, so copper goes to +2, so that's oxidation. Silver 1 goes to silver solid, the silvery colored silver, that's reduction, right? So you can split them into two half reactions. Here's my copper to copper 2 oxidation half reaction. Here's my silver 1 to silver half reaction. And we see that copper is oxidized. So that makes copper the reducing agent, right? If you are oxidized, you are reducing the other guy, so you are the reducing agent. That makes silver then, because he's reduced, the oxidizing agent. So we want to be able to recognize half reactions, recognize redox in the first place, and then identify reducing agents and oxidizing agents. One more example. We saw this one already. So here we identified that zinc goes to zinc +2, and that is oxidation. Copper 2 goes to copper 0, that's reduction. All right, so if zinc is oxidized, that means he's the reducing agent. If copper 2 is reduced, that means copper 2 is the oxidizing agent. All right, so thinking back, we can recognize these reactions now as either think of them in terms of numbers of reactants and products, so combination, double displacement, single displacement, decomposition, or we can think about them as precipitation, redox, or acid-base. So take a second to try to identify these reactions. All right, the first one looks to me like calcium nitrate, sodium carbonate, and they switch partners, don't they? So this is double displacement, And aqueous goes to a solid. That's also a precipitation reaction. So precipitation or double displacement, it's both of those. Here we have NH3 gas reacts with HCl gas to make NH4 plus Cl minus. That looks like one thing and a couple. Now I get a couple and one thing. So NH4, he got the H. So this looks like single displacement to me. Really what happens is these guys will find each other and you'll make ammonium chloride solid, but it's a single displacement reaction. It's also, HCl is an acid, ammonia is a weak base. So this is both an acid-base reaction and single displacement. Zinc solid reacts with HCl to make H2 gas, classic single displacement, and redox, isn't it? Zinc is being oxidized. So redox, hydrogen displacement, single displacement reaction. What about this? Calcium and fluorine react to make calcium fluoride. Looks like combination. And is it redox? Let's check. So calcium goes from 0, solid, to +2 as an ion. It is. It's redox. So both redox and combination. All right, so we can recognize those reactions that way. Finally, just a real-world example that they don't use anymore. But this is how a breathalyzer used to work. Now they use infrared spectroscopy. But here we have an alcohol, ethanol, right? A 2-carbon alcohol. When it sees potassium dichromate, right, it reacts. This guy is oxidized. So that means chromium should be reduced. And this is what we see. We could take the time to figure it out, and you should probably do this. It goes from +6 to +3. That's reduction, in fact, right? And it turns out that chromium, when he's +6, is kind of orange. When he's +3, he's green. So what they've done in this apparatus is they've got a thing that measures the orangeness, basically, right? And as that orange disappears, right, there's a detector that tells you that, oh, there was enough alcohol in there to reduce chromium-6 to green chromium-3, and you're going to jail. All right, we're going to take a look at bologna sandwiches next.